All right, get ready to explore because today we're going deep, like really deep, into the world of protons.
Deep dive indeed.
These tiny particles, the ones that team up with neutrons to form the nucleus of every atom. Turns out they're not as well understood as we thought.
Not quite, no. They've been giving us quite the headache, actually. A real proton puzzle, you might say.
A puzzle.
Mm.
Okay, now I need to hear more. What's got physicists so perplexed about these tiny particles? I thought we had them pretty much figured out.
Well, imagine trying to figure out the shape of something you can't even see, like a room, but you can only throw bouncy balls inside and see how they bounce back.
Okay, I guess that's kind of how we picture scientists probing the atom, right?
Exactly. That's essentially what we do with electron scattering. We hurl electrons at protons and observe how they scatter to get a sense of their structure.
So we're playing subatomic billiards to unveil the secrets of the proton. I like it. But how do we translate those scattered electrons into actual information about the proton itself?
That's where form factors come in. Think of them like a fingerprint, a mathematical description of the proton's internal structure. They tell us how the electric charge and magnetism are distributed within the proton.
Ah, so it's like we're creating a map of the proton's insides, revealing its hidden architecture. Form factors, the cartographers of the quantum world.
Yeah.
But you mentioned a puzzle. What's so puzzling about these form factors?
Here's the thing. For years, we were getting conflicting results depending on how we measured these form factors. It was like getting two totally different maps of the same room.
That is a head-scratcher. How could that be possible? Was it a measurement error? Or did we just completely misunderstand something fundamental about how protons behave?
Well, that's the million-dollar question, isn't it? Scientists were stumped for quite a while. But then a possible explanation emerged. Two-Photon Exchange, or TPE for short.
Two-photon exchange. Okay, you're going to have to break that down for me. I'm picturing photons as these tiny packets of light, right? What do they have to do with protons?
You're on the right track. You see, up until that point, we assumed that when an electron interacts with a proton, they exchange a single photon, like a tiny game of catch.
So it's like our subatomic billiard balls. Each collision transferring a single photon, carrying energy and momentum. Simple enough, right?
Not so fast. TPE suggests that sometimes, instead of just one photon being exchanged, two photons get involved in the interaction.
Two photons. So it's like those billiard balls are suddenly passing a basketball back and forth in the middle of their collision.
It's a bit of a mind-bending concept, I'll admit. But remember, we're in the realm of quantum mechanics here, where things work a bit differently than in our everyday world.
Quantum mechanics always full of surprises. But if this TPE idea, this two-photon exchange, could explain the discrepancies we were seeing in those proton measurements, well, that would be huge. But how do you even begin to test something like that? We're talking about interactions at unimaginable scales.
You hit the nail on the head, and that's what makes the experiment we're about to delve into so incredibly ingenious. A team of physicists at the Thomas Jefferson National Accelerator Facility, or Jefferson Lab as it's commonly known, designed a remarkably precise experiment to put this TPE theory to the test.
Jefferson Lab. Now that's a name synonymous with pushing the boundaries of physics. All right, let's hear it. How do you shine a light, or should I say, two photons, on this two-photon exchange mystery? What did they do? Okay, lay it on me. What was their master plan at Jefferson Lab? How do you go about observing something as elusive as a two-photon exchange?
Well, they took a very clever approach. Instead of just using electrons, they decided to compare how electrons and their antimatter counterparts, positrons, scatter off of protons.
Wait, are we talking antimatter here? I thought we agreed no explosions in this deep dive.
Don't worry, everything was perfectly safe. But you're right, antimatter does have a bit of a dramatic flair to it, doesn't it? It's like the Hollywood version of particle physics.
Okay, so remind me, how do positrons fit into all of this?
So basically, every particle has an antiparticle. It's sort of mirror image. Same mass, but with the opposite charge. A positron is like an electron, but instead of a negative charge, it has a positive charge.
Right. I think I'm remembering that from way back in my physics class days.
Yeah.
But how do positrons, antimatter or not, help us unlock the secrets of this two-photon exchange business?
Well, the theory goes that TPE would affect how electrons and positrons scatter off protons a little bit differently. It's a subtle effect, but measurable. Think of it this way. If you throw a tennis ball with a spin, it'll bounce off a wall differently than if you throw it without a spin, right?
Gotcha. So by looking at the differences in how the electrons and positrons scatter, they were looking for those subtle fingerprints of TPE. Clever.
Exactly. But I'll tell you, actually creating a beam of positrons, well, that's not exactly a walk in the park. Antimatter, as you can imagine, is pretty rare, and it has this annoying habit of annihilating when it comes into contact with matter. Not exactly ideal for a controlled experiment.
It's putting it mildly. So how did they manage? Did they have some kind of like antimatter containment field, something out of Star Trek?
Not quite Star Trek level tech, but impressive nonetheless. What they did was actually quite ingenious. Instead of switching back and forth between beams of electrons and positrons, which can introduce a lot of uncertainty, they created a mixed beam with both.
A mixed beam. Sounds chaotic, like trying to herd cats, but with, subatomic particles.
Controlled chaos, perhaps? But seriously, by using a mixed beam and carefully accounting for those subtle differences in how electrons and positrons interact, they were able to get much more precise data. It's all about minimizing those uncertainties and really isolating the effect you're looking for.
Okay, so we've got our mixed beam, electrons, and their antimatter buddies, all lined up and ready to go, aimed at. What exactly? What are these particles colliding with?
They aimed this beam at a target of liquid hydrogen.
Liquid hydrogen. Now that sounds intense, like rocket fuel, kind of intense.
It is pretty intense when you think about it, but in this case, it's a very dense source of protons, our targets of interest. Imagine like a proton shooting gallery.
I like it. And I'm guessing they didn't use your average high-speed camera to capture all the action.
Right. Not quite. They used a truly remarkable detector called TLS, the CBAF Large Acceptance Spectrometer.
Bitchy name. What's so special about this CLAS?
Imagine a giant multi-layered camera, but instead of capturing light, it captures the trajectories and energies of those scattered particles with incredible precision. It's like having a front row seat to the subatomic mosh pit.
Wow, they're tracking particles 1,000,000,000 times smaller than a grain of sand. It's mind-boggling.
It really is amazing when you think about the scale of it all. But even with this incredibly sophisticated setup, minimizing bias in the experiment was absolutely crucial.
Bias. I thought we were talking physics here, not a court of law.
Good point. You're right. But in physics, bias refers to anything that could skew the results, any factor that might give us a misleading picture of what's really going on. And remember, electrons and positrons, they don't always play by the same rules.
Right, like those spinning tennis balls bouncing in their own unique way.
Exactly. So the researchers had to account for those differences meticulously to make sure they weren't introducing any unintentional bias into their measurements. They even developed sophisticated algorithms to simulate the paths of the particles, making sure that the analysis was completely fair and unbiased, like calibrating a super sensitive scale.
So they've accounted for every variable, eliminated every potential source of bias. Sounds like they really went the extra mile to get this right. After all that work, all that planning and execution, what did the data actually show? Did they find evidence of this elusive two-photon exchange? All right, the moment of truth. After all that meticulous planning and experimentation, what did the data at Jefferson Lab reveal? Did they find evidence of this elusive two-photon exchange?
Well, the results were pretty amazing, to say the least. The experiment definitely showed strong evidence that TPE plays a significant role in electron-proton scattering.
Wow, so it wasn't just a theoretical quirk after all. They actually found proof of this two-photon interaction.
Exactly. And it wasn't just about confirming TPE either. The findings also challenged a long-held assumption in physics. See, for a long time, we thought that at very high energies, protons basically behave like point-like particles with no real internal structure.
So instead of those tiny billiard balls we imagined, the experiment revealed something a bit more interesting.
You could say that. The data suggests that even at these unbelievably tiny scales, protons are way more complex than we initially thought. It's like, imagine thinking you're looking at a perfectly smooth surface, but then you use a magnifying glass, and suddenly you see all these intricate patterns and textures you never even knew were there.
That's incredible. So this two-photon exchange is essentially giving us a whole new perspective on the very building blocks of matter. What kind of patterns did TPE uncover? What's this telling us about the structure of a proton?
It's kind of like we had a two-dimensional image of a proton before, and TPE is allowing us to see it in 3D for the first time. The data indicates that the way electric charge and magnetism are distributed within the proton, it's not uniform like we once assumed. It's much more complex and dynamic than we ever imagined.
Wow, so protons are more like bustling, intricate cities than simple solid spheres. It really makes you wonder what other secrets are hidden within these fundamental particles.
You said it. That's what's so exciting about scientific discovery. Often, uncovering one mystery just leads to a whole bunch of new questions, new avenues to explore.
So what are the next steps? What new questions are these findings raising?
Well, for one, there was a really interesting trend in the data. As the energy of the electrons and positrons increased, the effects of TPE became even more pronounced.
So the faster those particles collide, the weirder and wilder this two-photon exchange gets.
Pretty much. It's like we've just scratched the surface of understanding this phenomenon. Investigating what happens at even higher energies, that's a really exciting avenue for future research.
That's incredible. It really goes to show that even in the seemingly well-charted territories of physics, there are always new mysteries waiting to be uncovered. And it seems like this two-photon exchange is opening up a whole new chapter in our understanding of the subatomic world. Well, this has been an incredible journey. From throwing metaphorical tennis balls at car engines to unraveling the intricate dance of two-photon exchange inside a proton, we've really gone deep today. And it's a good reminder that the universe is chock full of surprises, and the more we explore, the more we realize just how much more there is to learn.